Hello, Kip. How are you?
Good. How are you, Miguel?
Fine, thank you. Happy to have you here with us.
Well, it's a pleasure and an honor. Thank you.
It's really an honor for us to have you here. We've been trying to invite you for a while. It's great that it finally happened, even if it's like this, like virtually.
Yeah, well, I think you know my brother lives in Mexico, and I do spend a lot of time there, down in Nayarit, but not during the pandemic.
Yeah, exactly. Yeah, it's about time. So we're just waiting for Tonatiuh Matos. Apparently he's connecting just now. He's
Yes,
the president of the Mexican Physical Society, as you know, and I guess he'll tell us when to start.
Okay.
Tonatiuh, you have your microphone off, Tonatiuh, I think.
Yes, now, no? Yeah.
Yeah.
Yeah, thank you. Thank you for accepting our invitation.
Well, it's a pleasure. Thank you.
Yes. Well, the way to proceed is we will, you will give your talk after Miguel presents you. I will speak a few words about some the Nobel Prizes and something like that in Spanish, very, very, very shortly. And after that, you can give your talk.
Okay.
In 3 minutes we start. And what about the interview in this newspaper?
I think I said I would do it. I'm not dealing very well with email. They might have contacted me, but I didn't notice it. Were they going to email me, or what?
No.
How was this going?
No, we can arrange a time when you have time to give this interview. For example, after this talk could be a very good time, or tomorrow maybe, or something like that. When whatever you want.
So after this talk, I'm free only until 6 p.m. my time, 8 p.m. your time, approximately. So tomorrow might be better, but.
Okay. When do you have time tomorrow?
I'm completely flexible tomorrow. Anytime that works for them.
Okay.
With me.
Okay. Then maybe tomorrow it's better. Okay.
Yeah.
Mm-hmm. Okay. Maybe I send you the an appointment for tomorrow by email, and then we can arrange the time. Okay.
If you need any help with the interview, Tonatiuh, just let me know. So
yes, of course.
Connect. Yeah.
Yeah, of course. Yes. It will be so that Miguel and me will be together with you tomorrow in order to help this guy to give the interview and something like that. Okay.
Good.
The translator to make sure they don't ask something very strange.
Yeah. Yes.
Well, it's shameful that I speak almost no Spanish. But,
yeah. No. He should speak English, of course.
Well, I should speak Spanish. Living in the U.S. and spending a lot of time with my brother in Mexico, but I know just the most rudimentary, enough to get along in a restaurant. That's about it.
Yes. Miguel and me, I written a popular book about wormholes and warp drive. Maybe in the next year I will present this book for you. In Spanish, of course. But.
You're always welcome to come here in Mexico whenever the pandemic is over. Really love to have you here.
I hope that my bandwidth is okay. It says my internet connection is unstable, and it's usually better than this. But are you having trouble with my transmission? Is it all right?
No, not till now. No, I don't think.
No,
it's okay. I think.
I think it's reasonable. It's a little bit broken, but not bad. I think it's reasonable.
Yeah, I'm sorry. I don't know what to do about it. I can move the transmitter in another room where I don't know where its signal is coming from. So I'm in a rural area in Oregon, and our internet is not as good as it should.
Yeah, it's been very different now with the pandemic, right? I had to put internet transmitters in every room in my house now. Because we're connected all the time. Myself, my wife, my daughter, so everyone's connected.
So I wonder if I should
Donatium. Doctor,
Sí,
¿comenzamos?
No.
Son
So
las
I think my problem may be
Estamos
people
listos
coming
cuando
in.
usted desee, cuando usted guste, doctor. Adelante.
Okay. Well, it's time to start, and then I will introduce you with the people in our community, okay? And then Miguel.
How much time do we have? Should I experiment with this?
Well, the time you need, for example, 1 hour for your talk or something like that, around that, and after that, maybe half an hour or 20 minutes questions. You decide that, okay? And yeah, please. Okay. Well, then we start now, yeah? Okay. Bueno, buenas tardes a todos. Tenemos ahora la plática del doctor Keith Thorne. Él es Premio Nobel del 2000.
I'm just...
¿Sí? ¿Iba a decir algo?
Sí, pero parece que ya. Sí.
Hay un problema en la conexión del doctor.
Hay problemas de conexión.
Sí. Just a moment. I think I know how to fix this, but I'm not sure. Just give me a minute here.
A ver, vamos a esperar un momentito que él conecte bien su...
If you give me a couple of minutes, I may be able to solve this.
Okay.
Very sorry.
Bueno, voy a empezar con la presentación del doctor Thorne mientras él se conecta bien. Ok, esta es una plática de Premio Nobel. Como todos los años tenemos una plática de Premio Nobel. Espero que la... Ajá. Sí, todavía no se conecta bien, ¿eh? Sigue teniendo... Se corta.
I'm having real trouble, but I think I...
Can you hear me, Professor Thorne?
I can hear you. I can hear you.
Okay.
I'm trying to connect to my cell phone company. It's not even connecting in there. So it may take 5 minutes. I don't know. Let me, while it's trying to connect, let me see if I can get on my wife's.
Okay.
Caroline. Sarah Lee, can you bring your computer in? Never mind. Can you bring your computer in here?
No solo en México pasa.
Never mind, I'm getting in. Never mind, Caroline.
Okay.
So I'm.
What do you need?
Okay.
You want me to get off?
I apologize, but I think I can solve this.
You want me to get off?
Yes, please.
Okay. Did that help?
I don't know. So is that any better, Miguel?
Yes.
Yes, I can see you and hear you fine.
Yes.
Okay. I'm still trying to, give me another minute or two here.
Mm-hmm.
Okay, I think I've solved it. Let's hope so.
Yes, it's reasonably good, your connection, I think. I can hear you
See.
well. Yes.
Okay. So
Yeah.
let me just. Okay. I think we can go ahead.
Okay, then let me start then. Bueno, les estaba diciendo que esta es una plática de Premio Nobel. Esta es de una serie de pláticas que tenemos cada año. Este año le toca al profesor Kip Thorne, es Premio Nobel del 2017. Él es, tal vez se puede decir, el primero de un grupo de una racha muy buena para cosmología y gravitación. El año de 2017 fue Reinhard West, Barry Barish y Kip Thorne, que obtuvieron el premio Nobel por las ondas gravitacionales, y el año 2019 fue James Peebles por las fluctuaciones del universo para explicar el comportamiento del universo como lo vemos, o sea, la estructura a gran escala. Y este año, pues Roger Penrose obtiene el premio Nobel por la deducción de los hoyos negros como cosa completamente explícita en las ecuaciones de Einstein, junto con Andrea Ghez y Reinhard Genzel, que encontraron el hoyo negro supersimétrico en el centro. Bueno, pues esta es una plática, se las recomiendo mucho, es muy interesante. Seguramente va a hablar sobre agujeros de gusano. Esa es una de las cosas que quedan pendientes de descubrir en la relatividad general. Entonces, por favor, Miguel, si tú lo quieres presentar, yo me hago un ladito y ustedes ya platican, ¿sí?
Claro.
Thank you very much, Professor Thorne, for accepting our invitation. You are now here. Miguel will speak about that. Okay.
Well, I'm going to say a few words in English and then I'm going to move into Spanish. So first of all, I want to thank Professor Tonatiuh Matos for giving me the honor to present our distinguished speaker, Nobel Prize winner, Professor Kip Thorne. Thank you, Kip, for being here.
Thank you very much. Can you hear me?
My Physics Society to have you here today. I hope you don't mind. I will make your introduction in Spanish, and I'll just speak for a couple of minutes about what you have done in your career. Entonces, muy buenas tardes a todos. Primero que nada, quiero agradecer al doctor Tonatiuh Matos por permitirme presentar a nuestro distinguido invitado el día de hoy, a quien con toda seguridad todos ustedes conocen. El profesor Kip Thorne es Premio Nobel de Física 2017, junto con Rainer Weiss y Barry Barish, por sus contribuciones decisivas al desarrollo del proyecto LIGO, el Observatorio Gravitacional por Interferometría Láser, y la primera observación de ondas gravitacionales. El profesor Thorne obtuvo su doctorado en la Universidad de Princeton en 1965, bajo la supervisión de John Wheeler. En 1967 se incorporó como investigador al Instituto Tecnológico de California, Caltech, donde ocupó la cátedra Richard Feynman desde 1991 hasta su jubilación en el 2009. De entonces a la fecha es investigador emérito de ese mismo instituto. La investigación del profesor Thorne se ha centrado principalmente en el estudio teórico de la emisión de ondas gravitacionales por distintos sistemas astrofísicos, campo en el cual ha hecho numerosas contribuciones seminales, muchísimas como para enumerarlas aquí. Pero en particular puedo mencionar que fue uno de los 3 proponentes del proyecto LIGO a fines de la década de los 80s, proyecto que daría lugar a la construcción de los primeros grandes interferómetros para observar ondas gravitacionales y que culminaría con la primera detección histórica de ondas gravitacionales provenientes de la colisión de 2 agujeros negros en septiembre del 2015. Este fue el motivo de su premio Nobel 2 años después. El profesor Thorne también realizó estudios fundamentales en la física de agujeros negros. Fue uno de los creadores del famoso conocido paradigma de la membrana, que se utiliza para estudiar estos objetos. También es el autor de la muy famosa conjetura del anillo, o Hoop Conjecture en inglés, que dice que si un objeto puede ser rodeado por un anillo de circunferencia igual a 2π veces su radio gravitacional, entonces dicho objeto colapsará a un agujero negro. Por si fuera poco, en la década de los 80s, el profesor Thorne publicó varios trabajos donde estudiaba la física de agujeros de gusano, también conocidos como los túneles de Einstein-Rosen. Más recientemente, el profesor Thorne fue el asesor científico y además el escritor del primer guión de la película Interstellar. Es además coautor, junto con John Wheeler y Charles Misner, del famosísimo libro Gravitational, la Biblia de la gravitación, que se ha convertido en una de las referencias fundamentales en el estudio y en la enseñanza de la relatividad general. Ha escrito varios libros de divulgación, entre los que podemos mencionar La ciencia de la película Interstellar y el libro Agujeros negros y curvatura del tiempo. En una nota mucho más personal, el profesor Thorne fue asesor de doctorado de Bernard Schutz quien a su vez fue mi asesor de doctorado. Debido a esto lo conozco personalmente desde hace casi 30 años y siento una profunda admiración y respeto por él. Los dejo entonces con el profesor Kip Thorne. I leave you then with Professor Kip Thorne. Kip, thank you very much, and go ahead as soon as you want.
Okay, thank you very much. It's a great pleasure to be here. Can you hear me okay?
Yes.
Yes. Well, I apologize if my connection is not very good. I'm coming in from a very rural area in Oregon in the United States, and I've been having some trouble today with my connection. Today, I would like to talk about my 60-year romance with the warp side of the universe. So I'm going to share my screen with you. Okay, can you see my screen okay? So, and I will also discuss some lessons that I have learned. But could, so Miguel, can you hear me all right? I'm just concerned about my connection.
Yes, we can hear you.
Okay, fine, thank you. When in 1953, yes, okay. In 1953, when I was 13 years old, I found in a bookstore a book by the cosmologist George Gamow titled 1, 2, 3, Infinity. And in this book, I learned about warp space and warped time and general relativity. And I became totally enamored. I loved the ideas of relativity. And so when I finally got to graduate school, I chose to go to Princeton University to study with John Wheeler, who was the best expert in that period on Einstein's relativity theory. And I learned from Wheeler about what I like to call the warped side of the universe. And by this, what I mean is objects and phenomena that are made from warped space-time. Let me tell you more particularly what I learned about. First, let me think about our universe as being two-dimensional, a two-dimensional surface in a higher dimensional space, what physicists may sometimes call the bulk. If it is bent around as I show it here, then I can imagine a black hole around which space is warped, and so it looks like this. So I learned about black holes. I learned about singularities inside of black holes. I learned about wormholes that connect two different regions in our universe. I learned about the dynamics of warped space-time, call it geometrodynamics, the dynamics of the geometry of warped space-time. And I learned about gravitational waves, and also about the possibility of closed time-like curves or backward time travel. And so I want to tell you in this lecture about what I have learned in that period since then, that's more than 50 years ago, what I have learned about the warped side of the universe, working together with my students, my colleagues, and work by others among my colleagues. Let me go back to 1939 with Robert Oppenheimer and his student Hartland Snyder, who studied the possibility of the collapse or implosion of a star. They idealized the star as a ball of dust with vanishing pressure, and they solved Einstein's equations of general relativity to study how it collapsed, shrinking inward and inward. And they discovered, to their great surprise, that when it reached a certain size, called the gravitational radius, at the surface of this object, time seemed to slow to a halt, and gravity was so strong that nothing can escape. In Oppenheimer's words, the star cuts itself off from the rest of the universe after it passes through this surface. John Wheeler, my thesis advisor later, some years later, he fought against this from 1953 until about the time that I met him and started to work with him in 1962. And then he embraced this prediction and began to call this object a black hole. In the 1950s, Wheeler thought, however, that wormholes were more likely to be real. He was very skeptical about this object he would later call a black hole. And so I would like to describe what we learned about wormholes, beginning with his work, well, in fact, a little earlier, with work of Albert Einstein and Nathan Rosen in 1937. In 1937, they realized that Schwarzschild's solution to the Einstein equations this can be viewed as describing a wormhole, a connection between two asymptotically flat spaces, which could be different regions of our own universe. And this came to be called an Einstein-Rosen bridge. Wheeler became very excited about this in the mid-1950s. And he speculated, among other things, about the possibility that electric fields could thread through this wormhole, as he called this object. And so you would see electric field lines coming out of one mouth. This is his own drawing of this wormhole, and travel down into the other mouth. And so this would look like an electron, and that would look like a positron connected by electric field. He called this charge without charge, particles without particles, the electric fields without having any particles present. More exciting to him, I think, and to us in subsequent years, was the idea that there might be fluctuations in the topology of space and time, what he called quantum foam of wormholes, where there might be, for example, on the scale of the Planck length, or I like to call it the Planck-Wheeler length, 10 to the minus 33 centimeters, there might be a 3% probability for this kind of a structure of wormholes down on that very small scale, a 5% probability for this, I apologize, and a 1% probability for that. To Wheeler's amazement, however, a few years later, largely through the work of Martin Kruskal, who was a young colleague of Wheeler's at Princeton, this is 2 years before I arrived, he discovered by rethinking the Schwarzschild metric of general relativity from a different point of view and different coordinate system, that a wormhole will pinch off before anything can fall through it, a Schwarzschild wormhole. So if you had a photon trying to travel through this wormhole, the wormhole would shrink and implode, and the photon would be caught in the implosion. It would not be able to travel across, and you would wind up with two singularities in these two different regions of space. This then finished wormholes as something on a classical scale that Wheeler thought would likely occur, though he still expected it to play a major role in quantum physics down on the Planck scale with quantum foam. 25 years later, when I had also totally lost interest in wormholes, the astrophysicist Carl Sagan telephoned me. He said he had written a novel called Contact, which later became a movie with Jodie Foster. And in this novel, he had his heroine traveling through a black hole to get near the star Vega. And he said, I realize I may be in trouble. You're a better expert about relativity than I am, he said to me. And so he asked me for help. And I told him, well, obviously what he needed was a wormhole, not a black hole. And so you had our solar system up here in the Earth, and instead of traveling 26 light years to get to Vega, his heroine, Jodie Foster, traveled down through a wormhole to get to Vega. It was then for the first time that I began to think about wormholes, not Schwarzschild wormholes, about the issue of, do the laws of physics permit an arbitrarily advanced civilization, as in this novel Contact in science fiction, permit a civilization to build and hold open wormholes for rapid interstellar travel. So this was the issue then of traversable wormholes, wormholes that you could travel through. And that was then when I, and then following me, a number of other people started studying the possibility of wormholes. It very quickly became obvious to me that there was a major problem with holding a wormhole open. If you take a light beam and you send it radially into the wormhole, initially the light beam is converging. Its surface area, its cross-sectional area is decreasing. And then when it comes out the other side, it's increasing. This is just the opposite what happens with the focusing of a light beam by the sun. The light beam may come in with parallel light rays, be bent around the sun by the sun's gravitational field and be focused. And what is it that does the focusing? Well, it's the matter, or more precisely, the mass of the sun. Or more precisely, when you look at it very carefully, it is the basically the mass that's there as seen by somebody who moves at nearly the speed of light, traveling along these light rays. And so it became obvious that a traversable wormhole must be threaded by material that repels gravitationally, that has negative energy, at least when you look at it in Einstein's relativity, at least negative energy averaged when you travel along one of these light rays at nearly the speed of light and add up the energy that is encountered, needed to be negative. It was a little later that I discovered that I was not the first person to realize this. Dennis Gannon probably was in Journal of Mathematical Physics about 10 years earlier. Let me just remark that in my own experience, it's frequently that I discover something that somebody else has previously discovered. The joy of the making a discovery is no less when it's just for myself and somebody else has discovered before. Just the thrill of suddenly understanding is still equally good, even though I realize afterwards that somebody else has understood it. Exotic matter actually does exist due to vacuum fluctuations. I remind you that if you take a box and you remove everything that you can possibly remove, then vacuum fluctuations of all types of fields that can exist, electromagnetic fields, gravitational fields, neutrino fields, vacuum fluctuations remain. They have zero net energy after renormalization in quantum field theory, and they do not gravitate. At least that's what theory says. We don't have an observational proof they don't gravitate. And so suppose that I have then just vacuum fluctuations. These are two neighboring regions of space. And suppose that the right region borrows some energy, borrows some vacuum fluctuations from the left region. Then the right region has gained net energy, so it has positive energy, and the left region with lower vacuum fluctuations is left with negative energy. And so this is the key to making exotic matter. You have to take vacuum and have one region borrow fluctuations from the other region. A good example is the Casimir effect of electrically charged plates, electrically conducting plates, and they, it turns out, attract each other. And so if you take handles and attach them to the plates, and you let the plates come together, plates as they come together will do work on your hands. And you'll be left with negative energy between the plates in the vacuum electromagnetic field and a net increase in the energy in your hands. This comes about actually, of course, because there's a boundary condition on these plates that parallel to the plates, the electric field has to vanish. And so that suppresses the vacuum fluctuations between the plates, causing them to have net negative energy, to be exotic. So that is a good example of vacuum fluctuations being changed so they have negative energy. So the question arose, can an infinitely advanced civilization collect enough exotic matter in a wormhole's throat to hold the wormhole open? And there has been a large amount of work on this since my students and I started asking that question back in the late 1980s. But the bottom line answer is not clear, nevertheless. The answer is probably not. There's a nice little book by Alan Everett and Thomas Roman titled Time Travel and Warp Drives, in which you can go in and read semi-technical discussion of the attempts to answer this question. An enormous surprise to me came in 1994 when Miguel Alcubierre, who introduced me, then he was a student, I believe, at Cardiff University in Wales in the United Kingdom. he devised a solution of Einstein's equations that described the possibility of traveling faster than the speed of light by warping space and time. What he said is, in this solution that he wrote down, is that if you want to travel far faster than light relative to things in the rest of the universe, and if you have the adequate technology, then all you need to do is cause space to contract in front of your spaceship. So this is plotting downward the rate of contraction of space. This is from Miguel's article, which is you can read on the Physics Archive at that location. It's a wonderful little article. The rate of contraction of space is very big rate of contraction of space in front of the spacecraft, and a very big expansion of space behind the spacecraft. And so you can sit inside here happily at rest inside the spacecraft, traveling far faster than the speed of light, because space in front of you is contracting. And so it looks to you like you're not traveling very fast at all because you're traveling through a very short distance, but that looks like a huge distance in front. Then you make up for it behind yourself by shoving all that space that was up in front back out behind. Do the laws of physics permit enough exotic matter for this? Again, probably not. People have attempted to answer that question. Again, there is some discussion in this book by Alan Everett and Thomas Roman. The lesson that I learned from this is the power of thought experiments to probe the laws of physics in domains where experiment is not yet possible. If you just pose a question and you ask, can an infinitely advanced civilization, a civilization that is constrained only by the laws of physics, can that civilization do something? You can actually learn amazing things about the properties of space and time. Along these lines then, another thing that my students and I asked was, do the laws of physics permit a very advanced civilization to construct machines for backward time travel? This is in Physical Review Letters back in 1989, work by my student Mike Morris and Ulva Yurtsiever and I. And this is a little space-time diagram from that article. I'll let you, as physicists, go read the article and look at the space-time diagram. It's just a space-time diagram for the twins paradox. And so the idea is this, in terms of a story. I take my wife, Carol Lee, I put her in a spaceship, I give her one mouth of a wormhole. She travels out at very high speed into the universe, comes back at very high speed. And in the process, then she ages much less than I do. So looking out through space as she is nearing home, she sees me very old. But during this trip, we may be holding hands and look at through the wormhole and looking at each other's wristwatches. And we see that time flows at the same rate inside the wormhole for both of our wristwatches sitting here side by side. So looking through the wormhole, she sees me as very young. So when she has returned, if I then go out and I squeeze myself through the wormhole, I'm now very old as she sees me. I go out as a very old man, squeeze through the wormhole, I can meet my younger self. The wormhole is now a time machine. So that was quite a surprise to us when we found that was true. And so we began, stimulated by colleagues, Robert Wald and others, we began to ask ourselves, is there some way that that might be prevented? Well, there's an idea that Bob Wald suggested to us. Send a pulse of laser light out through space and down into the wormhole and let it come back at just the same moment as it started out. Then you have two copies of that laser pulse side by side. And the two travel side by side, out and back, and you wind up with 3 or 4 copies of that laser pulse, and on and on and on. And there would obviously is an explosion of one laser pulse is turned into an infinite number of pulses in the end, ideally. Of course, that's not hard to prevent that from happening. You just put a wall around this wormhole, so no laser pulses can come out of the wormhole or go into that wormhole. But what you cannot shield out by a wall is very high frequency vacuum fluctuations. And so postdoc of mine, Song-Wan Kim, and I then did a calculation using quantum field theory in curved space-time, and found in 1990 that vacuum fluctuations will always go out and back in, and just at the time that this wormhole is becoming a time machine, they will pile up on themselves and create a diverging, renormalized energy density in those vacuum fluctuations. The problem is, however, that just at the time when that divergence of, when the vacuum fluctuations become strong enough to begin to destroy the wormhole, the laws of physics that we were using, quantum field theory and curved space-time, break down, and we can no longer use them for this calculation. They were replaced by the laws of quantum gravity. So is the explosion really strong enough to destroy the wormhole? Only the laws of quantum gravity know. I had long discussions in that era, 1990-91, with Stephen Hawking over this. He convinced me that the answer is controlled by the laws of quantum gravity, but he was essentially certain that wormholes will, that time machines will always destroy themselves when they're first turned on. And so he embodied this in what he called his chronology protection conjecture: keep the universe safe for historians by nature having a mechanism to always prevent closed time-like curves or time machines from being created. Let me turn to black holes now, something that we know observationally really does exist on the warp side of the universe. So the 1970s, I finished my PhD with John Wheeler in '65. The period from then on into the mid-1970s, a period when we were exploring, Stephen Hawking and I and others, my students, our students, exploring the properties of black holes. And we can describe the space-time curvature or warping of black holes in terms of three pieces: a warping of space, which is described by a three-dimensional metric. This is the space of an equatorial slice, a two-dimensional surface that goes right through the center of the black hole. Warping of time for somebody who hovers just above the black hole, moving inward slowly toward the horizon, the surface of the black hole. Time slows, there's a redshift, time slows to a halt. It stops flowing right at the surface of the black hole. This slowing of time is described what we call the lapse function, part of the full space-time metric. Inside the black hole, time flows in a direction you would have thought was a space direction toward the central singularity in the black hole. So that's really weird, but that's what the lapse function tells you happens. And then if the black hole is spinning, according to the so-called Kerr metric due to Roy Kerr for black holes, he discovered only in the late 1960s, the space is dragged into a rotational motion with an angular velocity that is larger near the horizon than it is farther away. And that's embodied in a so-called shift function in this space-time metric. What is it that warps space and time? It's the energy contained in the warping. The black hole is held together by its nonlinear self-interaction. It's what we would call a gravitational soliton. This is a precise depiction of the warped space around a non-spinning black hole, a Schwarzschild solution to the Einstein equations. The horizon is down here where the color is black. The colors show the lapse function, the rate of flow of time is 10% as fast where it's yellow as it is back on Earth. And it slows to a halt at the horizon, this black circle. Of course, it's a circle because I'm showing you only a two-dimensional surface through the equator of the black hole. It would be a sphere if I restored the third dimension. If the black hole spins rapidly, then the throat is much deeper. And in addition to the warping of space and warping of time, there's the angular velocity of the dragging of space or dragging of inertial frames, high near the horizon, low farther away like the air in a tornado. Let me say a few words about Hawking radiation for black holes. This is a lesson in the great power of physical intuition. Yakov Borisovich Zeldovich was a superb physicist in the old Soviet Union. In the period of from 1968 onward, I spent a lot of time in Moscow as a guest of Zeldovich and later of an experimenter named Brzezinski. And on a visit to him in 1972, he told me that spinning black holes will emit radiation because of quantum effects. I told him he was crazy. He told me that it's true. We made a bet. I lost the bet the following year. I lost it in a conversation with Zeldovich and Stephen Hawking in 1973. I came back again in that year. I brought Stephen Hawking with me. Zeldovich and his student, Alexei Starobinsky, sat us down and explained what happens. The basic idea is that whenever an object has energy that can be extracted, nature will find a way to do the extraction. And vacuum fluctuations are often a way that can do it, though other things may be stronger, more effective. If nothing else can do it, then vacuum fluctuations are likely to do it. An example is a fluorescent light bulb. In here you have a gas that has mercury in it, and you use an electrical discharge to excite the mercury atoms into an excited state. Then electromagnetic vacuum fluctuations come in from space around here. They tickle the mercury atoms and create stimulated emission. They convert vacuum fluctuations of photons into real photons. We call this also spontaneous emission, but spontaneous emission is really stimulated emission, stimulation by vacuum fluctuations to produce the spontaneous emission. Now, what Zeldovich said is, let's suppose that we have a rotating metal ball and the electromagnetic waves come in and there's spin energy in that metal ball. And so vacuum fluctuations, let me take it back, vacuum fluctuations can come in, they can swing around the metal ball, and they will extract energy from the spin of the metal ball, and they'll convert then virtual photons into real photons, vacuum fluctuations into real light. He said similarly, if you have a spinning black hole, the same thing will happen. The energy of the spin of the black hole will be sucked up by vacuum fluctuations. They'll be converted into real particles and will radiate. I was skeptical, like still skeptical, and then Starobinsky, Zeldovich's young colleague, showed us a calculation where that really happened. So a spinning black hole will emit all types of radiation, electromagnetic, gravitational, and neutrinos. Stephen Hawking went home to England and he thought about this, and he thought about this, and he thought about this. A few months later, he realized that vacuum fluctuations coming into a collapsing star that is collapsing and forming then a black hole, very high frequency vacuum fluctuations that have no trouble going through the material of the collapsing star, they will swing along the edge of the newborn horizon as just as it's being created and come out having been stimulated into real photons, real particles of all sorts. And this was Hawking radiation. Even a non-spinning black hole will radiate. This was phenomenal. That a spinning black hole would radiate, that was surprising, but not hugely surprising. This was phenomenally surprising, as we all know, and it's still regarded as quite remarkable, Hawking radiation from even a non-spinning black hole. But it was Zeldovich, through his amazing physical intuition, that he saw this would happen, even though he did not know relativity well enough to do a real calculation. Only his student could do the calculation. Let me turn to singularities. In September 1962, at my first meeting with John Wheeler, he gave me an inspirational private lecture about singularities. He said, let's go back to the calculation of Oppenheimer and Snyder, an imploding star, and it will implode down, it will form a black hole, and he said, at the center, there will be a singularity. And that he was not that interested in the black hole itself. He was interested in the singularity that formed at the center. He said, in this singularity, there will be what he called a fiery marriage of general relativity and quantum mechanics. And that is the place you should really look to discover new physics. The place where the laws of what we now call the laws of quantum gravity come into play. The impact of Wheeler's exhortations about this was enormous. Roger Penrose was a young mathematical physicist. In 1964, well, let me back up and say that most physicists, upon hearing Wheeler talk about this, said this has to be nonsense. In reality, the black holes are not going to form. In reality, there will be no singularity. This just can't really be true. Small deviations from spherical symmetry will cause the whole story to be changed. But Roger Penrose in 1964 did a remarkable calculation stimulated by Wheeler. He began by bringing the mathematical tools of differential topology into relativity. And then he used those to show that, that beginning with even a very highly distorted collapsing object, that you would still form singularities at the center, that it didn't matter whether it was spherical or not. And presumably you would form a black hole around there. What we now call cosmic censorship would say if you formed a singularity, then you also did form a black hole. But that does require the cosmic censorship conjecture to say it really is a black hole. Now, I think it was yesterday or the day before yesterday, the Nobel Prize was awarded to Roger Penrose for this work. The Nobel Prize Committee did not highlight the fact you need to invoke cosmic censorship in order to say that he was predicting a black hole. The cosmic censorship that you get no naked singularities, that if you form a singularity, you necessarily do get a black hole. The cosmic censorship is a very compelling idea. It seems to be almost certainly true. We have no evidence against it. And so in essence, he was predicting that black holes form even in highly distorted imploding systems. You get a singularity at the center and you get a black hole. And it was for this that Roger, very deservedly so, won the Nobel Prize 2 days ago. More precisely, what Roger proved is that inside here, some infalling photons cease to exist. There are time-like whirl lines that come to an end in finite proper time, in technical terms. But the big question was, then a lesson here is the importance of elegant mathematics. He brought in some very elegant mathematics and used it to prove something that nobody else had begun to be able to prove. And this was also then the foundation for work that he and Stephen Hawking went on to do to show that there really had also to be a singularity in the beginning of our universe in the Big Bang. But what was the physical nature of the singularity? The answer came, and the answer is not what I described at the beginning of my lecture, a little point there at the center. The answer came from 3 Russians, Vladimir Belinsky, Isaac Kalatnikov, and Yevgeny Lifshitz. This is John Wheeler. This is a very young Kip Thorne at the home of Kalatnikov with his daughter and his wife as well in 1971. And this is just shortly after Belinsky, Lifshitz, and Kalatnikov gave a proof with very complex perturbation theory calculations, interacting perturbations used in different regimes of the analysis. He proved that down at the center of the black hole, this is a depiction of the warped space around a black hole. At the center of the black hole, there's a chaotic singularity. More precisely, what they proved is that if I fall into that black hole, I'm stretched from head to foot and squeezed from the sides, then I'm stretched from the sides and squeezed from head to foot, back and forth, in a manner that is described by a mathematical map that is chaotic in the technical sense of the term of the words chaotic and the theory of mathematical maps. This was quite a surprise. It was chaotic in this way. It was also spatially a different pattern of stretch and squeeze at adjacent regions in space. But it was done, a calculation that was done using brute force computations with a number of different perturbation theory calculations in different regimes of the analysis. The mathematical physicists in the United States and in the United Kingdom were very skeptical. They loved the analysis of Roger Penrose, which was absolutely rigorous. This was not fully rigorous because it involved all these interacting perturbation theory calculations. However, Garfinkel at Oakland University, about 2 decades later, did numerical relativity calculations and verified that this, in fact, really is what happened. Walensky, Lifshitz, and Kalatnikov were correct. We now know, in fact, that there are 3 singularities inside black holes. In addition to the chaotic singularity, this is just a heuristic depiction of the chaotic singularity. There is the following, and I tell the story of this in semi-popular terms in my book about the science of Interstellar, the science in the movie Interstellar. Matthew McConaughey playing Cooper inside a spacecraft called the Ranger spacecraft goes into a black hole, and all of the things that fall into the black hole afterwards, even just vacuum fluctuations, but radiation, whatever, because time is so very much screwed up, so very much compacted inside here, is seen by Cooper. All of this stuff falls in a fraction of a second in a great sheet of energy falling in behind him. And Donald Marolf and Almosori, let me back up. This was proved by Eric Poisson and Werner Israel in 1994. And a decade later, Donald Marolf and Almosori proved, and these are perturbation theory calculations, that of all the stuff that fell into the black hole before Cooper did, some small portion will be backscattered and will come flying up to him, compacted into a thin sheet, a fraction of a second thick, a very thin sheet in the form of a shock wave. And so there's an outflying singularity, an infalling singularity, and a chaotic singularity. These outflying and infalling singularities occur so rapidly that the net amount of distortion of me, or of Cooper, if he gets caught by one of these singularities, is finite. Is the acceleration of his head relative to his feet, the tidal force, the tidal acceleration, diverges, but the second time integral of that, which is the net distortion of his body, is finite because this happens so rapidly. And so there is a question of what really happens after that. That this is a much more gentle singularity. There's much more gentle singularities than the chaotic singularity. And so that, in fact, is a challenge for the future. And a number of people now, including Franz Pretorius at Princeton, are beginning to try to figure out what is the connection between these 3 singularities. Is it like what I have drawn here in this heuristic diagram, or is it something different? Those singularities were only analyzed by perturbation theory. Well, these were also perturbation theory, but in the sense of Walensky, Kalatnikov, and Lifshitz. We need numerical simulations to really smoke out for sure what's going on inside of black holes. In 1971, John Wheeler, Richard Feynman, and I went to a restaurant called the Burger Continental in Pasadena, California. And sitting around at the table there, John Wheeler started to talk to Feynman and me about the Big Bang singularity at in the birth of the universe. And he said it seemed obvious to him that the laws of physics came into being. They were created in that singularity, along with all the matter and the radiation of our universe, all the material in our universe, that everything, including the laws of physics, were born in the singularity. And then he said, so what law is it that controls which laws get born? Feynman turned to me and he said, you know, this guy sounds crazy. But what you don't know is he has always sounded crazy. Back when I was a student, I learned that you should take his crazy ideas and unroll the layers of craziness, one after another, like the layers of an onion. And at the center, you will often find a kernel of deep truth. And I did that with his idea, Wheeler's idea that an electron is a positron. A positron is an electron going backward in time. And look what it got me. Well, we know what it got Feynman. It got him a Nobel Prize. So, and in this case, Wheeler's crazy idea, in fact, it is more or less the idea that has now become a major part of string theory. It's the landscape of string theory. Wheeler didn't know the details, but he had the general idea very amazingly back in 1971. So again, the lesson is the power of physical intuition if you have deep enough physical intuition. Let me turn to the dynamics of warped space-time. Wheeler, again, one of the inspirations that he gave to me and to his other students, his colleagues in the 1950s and 1960s, was that, and he gave this often in lectures in which he would put on the blackboard drawings beforehand, spend 2 hours putting drawings on the blackboard, and he would talk about them, because this was before the days of PowerPoint, before the days of view graphs. You just had blackboards. And what his inspiration was that the greatest challenge in classical general relativity is to understand the dynamics of warped space-time when black holes collide, the highly nonlinear behavior of warped space-time when it is highly excited, for example, by colliding black holes and changing very rapidly. And he said, for this, to explore this, we will probably need numerical simulations. And so numerical relativity was born then at the hands of his students, Charles Misner, Richard Lindquist, together with Susan Hahn from IBM in the 1950s and 60s. Bryce DeWitt took this up in the 60s and 70s, Ken Epley and Larry Smarr in the 70s, and a number of people on afterwards, including with the climax with Franz Pretorius, Joan Centrella, and Manuela Campanelli, who pulled off finally the first successful simulation of the collision of black holes orbiting each other and coming together and colliding. So let me describe the results then that were found for the geometric dynamics of colliding black holes. What I'm going to show you is simulations by Saul Tucholsky's SXS collaboration, simulating extreme space-times. Here is a drawing, a computer-generated movie of 2 black holes orbiting each other. They look like 2 funnels, similar to what I showed you before for the shape of space. They have the color coding is the slowing of time, where it's red, time is slowing, and black when you reach the horizon. And as these 2 black holes orbit each other and begin to merge, the shape of space creates a huge splash, like a splash in a storm in the ocean. And time oscillates, as shown by the color coding. And that splash and the oscillations produce gravitational waves that travel outward into the universe. That then was our first really beautiful example of geometric dynamics from a computer simulation. But this movie captures only a small portion of the space-time storm that's created by the black hole collision of geometric dynamics. In order to see other portions, it's necessary, it turned out, to visualize the Riemann curvature tensor of general relativity. This is the thing that embodies the curvature of space and time. And so this was work that was done by a number of Caltech postdocs and graduate students after some of them had moved off to other institutions and into South Africa. And so let me begin. The Riemann curvature tensor turns out to have two pieces. One is the tidal field that raises the oceans on the Earth if the tidal field is produced by the moon. And so what is it that raises the oceans? Well, it turns out if you visualize the Riemann tensor, as we have done, it turns out there are things that I would call tendex lines, tendex from the Latin word tendere, to stretch. Tendex lines that stretch toward and away from the moon. Of course, we understand this in Newtonian language, that this side of the moon is closer to the black hole than that side, or to this side of the Earth is closer than that side, and so gravity pulls more strongly on this side than on that side, and that causes the stretching. But in terms of the tidal field, there are tendex lines that stretch in this direction, and tendex lines that go through and stretch in that direction. These are, in fact, the integral curves of the eigenvectors of the tidal field, which is a second-rank symmetric tensor. The second piece of the Riemann tensor is something that I like to call the frame drag field. It's something that describes differential frame dragging. So if I put my wife, and she gave me her permission, at the north pole of a black hole, as the black hole spins, her feet are dragged around faster than her head. And so her head sees her feet going around counterclockwise. And if you think about that, that means that her feet see her head going around counterclockwise. And so there's a counterclockwise vortex of twisting space at the North Pole and a counterclockwise vortex of twisting space at the South Pole, a clockwise one at the South Pole, counterclockwise at the North Pole, clockwise at the South Pole. And there's a lesson here, the power of computer simulations. It was computer simulations that drove us to explore the properties of the, how to visualize the Riemann tensor. And it was computer simulations that showed us then what happens with these vortex lines. And let me go back, I'm sorry. The key thing is that there are also vortex lines that, guide these vortices of twisting space, counterclockwise, vortex lines for counterclockwise twist of space at the South Pole here, and for clockwise twist of space at the North Pole. So you have vortex lines guiding two vortices here. You have tendex lines that you can think of a bundle of tendex lines as being a tendex, a object that sticks out of the moon in this case, or out of a black hole in this case. So we have a black hole now. I have vortex lines sticking out of this black hole, and red vortex lines counterclockwise, blue clockwise. So the red vortex, the counterclockwise vortex is at the top here. The clockwise or blue vortex is at the top there. We're going to do a head-on collision in a computer simulation. This is the horizon of the black hole, color-coded with the kind of a vortex that's sticking out. So let me abandon the lines to just show you the color coding for the vortices that are sticking out. The collision occurs, black hole, now horizons have merged. We now have 4 vortices attached to this black hole. Vortices do not like to share a black hole. When a black hole is settled down into an equilibrium state, there will only be 2 vortices. So what happens? These vortices, it turns out, fight with each other. And here is the full simulation. Let's look up here in the upper right where it's blue, then it's red, then it's blue, then it's red. So the vortices fight with each other, they exchange direction of vorticity. And every time the color coding goes green, the vortex lines pop off of the black hole. It turns out they embrace each other, they form a torus, around the black hole of clockwise and counterclockwise vortices embracing each other. These tori travel outward one after another, each one weaker than the last one because the black hole is losing energy of oscillation to these vortices of twisting space. Just as a moving magnetic field creates an electric field by its motion, so these moving vortices create tendencies by their motion. And so this torus acquires tendencies that reach around the torus in this direction, that squeeze, and tendencies that stretch in that direction. And this combination of tendencies that stretch and squeeze, vortices that are clockwise and counterclockwise, all on this torus, these are gravitational waves. So let me talk now at the very end of this talk about gravitational waves themselves. 1972, together with my student Bill Press, I began to develop a vision for what you could do with gravitational waves if they could be detected. A vision for gravitational wave astronomy. This is from Annual Reviews of Astronomy and Astrophysics, 1972. Simultaneously, Ray Weiss, who was a friend of mine, we were both at Princeton together in the 1960s. He became a professor at MIT. He wrote a little technical progress report, which he distributed to his colleagues around the world as a preprint, in which he described a new kind of gravitational wave detector. He said, hang 4 mirrors by overhead supports along the arms of an L, perpendicular arms. When a gravitational wave comes by, it will stretch along this direction, pushing these mirrors apart, squeeze along that direction, pushing these together. The next half cycle, it will push these apart and these together. And you use a laser beam and laser interferometry to monitor that motion. I was in the final stages with Charles Misner and John Wheeler of finalizing our book, Gravitation, a relativity textbook. At the time I first heard this idea, I had not yet read Ray's technical paper. I had not yet had a chance to discuss it with him, but I heard the idea and it was obviously crazy. And so I wrote a little brief description of this idea in our textbook, and I simply said it is not promising. Why did I think it was not promising? It's because of the tiny motions that I expected would occur due to realistic astrophysical sources. You take 1 centimeter, divide by 100, you get the thickness of a human hair. Divide by 100 again, you get the wavelength of light. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of a nucleus of an atom. Divide by another 1,000, you get the mirror motions that I thought you might occur due to realistic gravitational wave sources. That was roughly 1 billion times smaller than the wavelength of the light that was to be used for this purpose. It was unbelievably small, and it was just hopeless, I thought, until I had long conversations with Weiss. I studied his paper, conversations with others, and I became convinced. And so I made a decision that my theory group and I would do everything we could to help him, Weiss, and his experimental colleagues succeed. It was a 40-year effort, took 70% of my research group's time and energy. So many things could go wrong that the interferometers became very complex, so complex that they have 100,000 data channels of data coming out of them. Only one of them is a gravitational wave signal. And it required the collective effort of 2,000 physicists and engineers, basically, to pull this whole thing off. Although the number of authors on the first paper were only 1,000. They were the people who were involved in finally making these detectors work. By 2015, we had 2 LIGO gravitational wave detectors, one in Livingston, Louisiana, the other in Hanford, Washington in the USA. And on September 14, 2015, as is well known, the first signal arrived. We call it GW 150914, named after the date that it arrived. The source was 2 black holes orbiting around each other, just as I described. And in fact, this movie I showed you is precisely for the source of that first signal, based on simulations that from numerical relativity. And in this case, the black holes were going around each other, and so the the vortices sticking out from the black hole's spin, instead of forming a torus, they just made a spiral arms. And as they traveled outward, they acquired tendices around themselves. And there's a second set of gravitational waves, tendices that stretch and squeeze from the newborn merged black hole. As the black holes go around each other, these tendices swing out and back. And they acquire, as they move, vortices of twisting space around themselves. So there are two families of gravitational waves that contributed to the signal that was seen. These gravitational waves traveled out of the galaxy in which they were born, into intergalactic space, across intergalactic space. And 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals, they arrived at the outer edge of the Milky Way galaxy. After 50,000 years, they reached Earth. They touched down on Earth at the Antarctic Peninsula, traveled up through the Antarctic Peninsula, this on the 14th of September, 2015, emerged through the Earth in Livingston, Louisiana at LIGO, stretched and squeezed these interferometer arms. They came up through the Earth at Hanford, Washington, stretched and squeezed here. The LIGO team, LIGO and Virgo team, of 1,000 people who were involved in the final payoff here, they analyzed the data and argued about it for 5 months before we finally announced the result. And when we announced the result, through comparing the stretch and squeeze, stretch up, squeeze down, from the signal as shown in gray with the numerical relativity in red, the comparison was absolutely perfect. And so long as these were two black holes, the initial black holes, 29 solar masses and 36, total of 65. Final black hole, 62 solar masses. 3 solar masses of black hole energy converted into gravitational waves and traveling outward in 1/10 of a second. So the total power output, the energy per unit time, 50 times larger than the total power output of all the stars in the universe put together, all coming from a distance of 1.3 billion light years. It was a remarkable discovery, a wonderful payoff. By now, LIGO and Virgo have seen several dozen black hole collisions, several neutron star collisions, possibly a black hole swallowing a neutron star. And by the 2030s, we will likely see waves 20 times weaker than today, every black hole collision in the universe, with masses less than 100 solar masses. So 400 years ago, Galileo built his little optical telescope and used it to discover the 4 moons of Jupiter, the brightest 4 moons, and created thereby electromagnetic astronomy. 5 years ago, LIGO turned on, saw gravitational waves from colliding black holes. Electromagnetic astronomy in 400 years has totally changed our understanding of the universe, an enormous revolution. And I invite you to speculate about what revolution will be caused that will arise from combined gravitational wave and electromagnetic observations in the next several hundred years. Thank you very much.
Thank you, Kip. I think it was a wonderful lecture.
Thank you. I'm trying to stop my sharing, but
so I guess we have some questions. I don't know if Tonatiuh has access to the questions there.
I don't have access to the questions. You're going to have to read them to me. My computer is maybe frozen up. I'm not able to stop sharing. Okay. Now maybe I can stop sharing. Just a second. No, I'm not. Okay. So you go ahead. You'll have. I will just listen to the questions. Can you still see me?
Yes.
Yes.
Yes, we can see you.
We can see you. We see your screen more than you. Yeah.
Yeah, I'm sorry. My screen is refusing to stop sharing. It's just frozen.
We can start with the question of Francisco Guzman. Jesús, can you, Francisco Guzman, Jesús, por favor, ábrele
Oh, that's me. Thank you. So, thank you very much for the talk, Professor Thorne. So, as a professor in Mexico, I would like to know something. I know gravitational physics occupies an important part of your heart. However, I would like you to mention 2 or 3 subjects within physics that you think our undergraduate students would like to be working on by 2030 or 10 years from now?
I don't have great wisdom about this. What I would like to say is that there are enormously exciting problems, research challenges in many different areas of physics and of science. I used to worry when I was young that I would not be able to find an area where there is elbow room, an area where I wouldn't. So my personality, I don't like to be in a crowded field. I don't like to be working on something and fear that somebody else will solve this problem before I'm able to solve the problem. So I wanted to find something where there were not other people really working on it. Turns out physics is so diverse that finding interesting problems that nobody else is working on is not all that terribly difficult. And that from condensed matter physics to interfaces with biology, biophysics, applied physics connected to engineering. I've worked in a number of other areas. I've worked in things related to geophysics. I've worked on the design of solid propellant rocket engines. I've worked in fluid mechanics in various applications. And I have found exciting things to do in all of these areas. And so rather than telling you specifically what are interesting things, I would just say, open your eyes and look at not just at fundamental physics, but all of the interfaces with all the other things in the world, interfaces with the weather, interfaces with the ocean, astrophysics, the physics of wood, the physics of rocks. There's fascinating things everywhere.
Thank you.
Okay. The next question is Juan Carlos del Águila. Juan Carlos del Águila.
Can you hear me?
Yes, now we can hear you.
All right. Thank you for such an interesting talk. My question is about wormholes. I have studied the Thorne metrics as part of my graduate work, and I have found that apparently some of these wormhole spacetimes can be linearly stable for non-radial perturbations. Additionally, phantom scalar fields are a likely candidate for dark energy, and they could be considered as the source of exotic matter for an hypothetical wormhole. So with these two possibilities in mind regarding stability and the gravitational source, can wormholes be thought of as a more realistic idea in physics? Thank you.
I think it's let me say that I have not followed in detail work on wormholes in the last 20 years, but it is certainly my impression that that there are possibilities here that we never dreamed of, from the kinds of work that you're describing, for example, and other work that's being done also on wormholes in the quantum domain. So when the efforts using quantum field theory and curved space-time made us start to be discouraged about whether or not you could have enough exotic material inside a wormhole to hold it open. I sort of turned my back on the subject. Well, I really turned my back on the subject because LIGO became hot. We got approved to construct LIGO just at the time I was finishing my wormhole work. So that's really the reason that I turned my back on it. But I was also a little discouraged at that point. But the kinds of things that you're describing have generated a new interest in this. And it does appear to me, looking in from the outside, like there are really interesting possibilities here. But I not followed in detail because my own research was driven into LIGO and then more recently into the numerical relativity simulations and extracting information from those.
Okay. The next question is from César Simón López Monsalvo. César López Monsalvo. César.
Yes, can you hear me?
Yes, we can hear you.
Thank you very much, Professor Thorne, for such an amazing talk. And my question is, we all love general relativity in a very different way. And there's a huge number of fantastic solutions that are not realistically feasible in gravitational physics. But yet, do you believe that some of these may find applications or could be viable within the realm of material science or analog models, so that these can be applied into, I don't know, optics or something?
Well, of course, there is this work connected with ADS-CFT, for example, that mapping of general relativity into and the equation of general relativity into the physics of other kinds of systems, and it's very possible. Well, we know there are examples of weird relativity solutions that really do have a relevance through this mapping to physics in other kinds of systems. And so there is a partial answer yes there, though it'll be some small fraction of all the known exact solutions in general relativity that will have those kinds of applications. My general, I have generally thought that it is more useful to focus in on problems that are actually occurring in physics in whatever field it is, and find approximate solutions that enable you to understand what's happening in the real world. That if you want to make connection with the real world, that approximation schemes are generally more powerful than exact solutions. There are big exceptions like the Kerr metric, and those exceptions are so few and far between that I think for a physicist, it's really, I think, important to also focus in on trying to understand things in the real world using whatever kinds of approximation techniques, numerical simulations, whatever is required to get down to the truth of what is happening in some particular problem or some particular area. On the other hand, there is great value in from the mathematical side in the exploration of exact solutions in order to get a deeper insight into general relativity itself, or possibly into other aspects of mathematics. But the exact solutions themselves, I think, very few of them will in the end be terribly useful in explaining things that we actually see in the laboratory or in the sky.
Yeah, thank you very much.
But just to reemphasize, there's enormous variety of different areas of science that one can go into, and the mathematical physics and exploration of exact solutions, there is real usefulness in that. That in itself is an interesting area, but it's an area that focuses on understanding the theory itself much more than understanding what we see around us.
Thank you very much.
Thank you very much.
The next question is from Miguel Mayorga. Miguel Mayorga. No, he's here.
Can you hear me?
Yes.
Okay. My question concerns with the information paradox concerning with the radiation of black holes and even with the collision of black holes. I mean, what about with the preservation of information? Or could you comment which is the role?
So I think the information paradox, let me just say a few words about the paradox itself first. The reason that this paradox is so important is that it seems to be digging deep into the heart of the connection between quantum theory and relativity, the laws of quantum gravity. Whenever you have a paradox of this strength that is at an interface between two areas of laws of physics, it's a wonderful tool for trying to understand the fundamental laws of physics more deeply. It was the paradox of what goes on at the singularity inside a black hole that Wheeler wanted to focus on back in the 1950s. This is the analog of that. And from this, I think we're going to learn very deep things about physics. I don't think the information paradox has been resolved, by contrast with Stephen Hawking, who felt it had been resolved. I don't think we really understand what's going on here very well. The one aspect of this that I, well, let me make several remarks about this. The vast majority of people working in this area are convinced that information does not get lost, that it all comes out in the end, and the radiation comes off of a black hole, and the black hole forms and then evaporates in the end. I am skeptical of that usual answer, and the reason is that I still think that John Wheeler's ideas about quantum foam are likely to have some truth to them, and that when you do calculations of probabilities in quantum gravity, if you do it by sums over histories, you have to include histories that have closed time-like curves. If you include histories that closed time-like curves, you end up with information being lost. Standard quantum mechanics cannot deal with that, but sum over histories of quantum mechanics of Richard Feynman can, and James Hartle and Murray Gell-Mann were the people who really developed this the farthest, I think. And in their formalism, their sum over histories formulas for quantum physics, information is lost, and it's a tool for actually exploring the loss of information. And so I have a minority point of view that says there's a very good chance that information is lost, and that the fundamental formulation of quantum physics is a sum over histories, and it's not the standard Hamiltonian formulation. They're equivalent in the absence of closed time-like curves, but they're not equivalent with closed time-like curves. With closed time-like curves, ordinary Hamiltonian quantum mechanics can't work, but the sum over histories can. So that's one aspect of my response. I'm wandering, but I'd just like to expose some ideas to you, motivated by the question. Another issue is there has arisen, because in the struggles to understand information loss, there has arisen the idea that there may be a firewall at the in place of a horizon, at the horizon of a black hole, that somehow, in order to deal with aspects of information loss, nature has to change the form and the properties of space and time very near a black hole horizon. And there's been a hope that that might show up then in gravitational waves that probe very close to a black hole horizon. If we had a very spinning black hole created with very high spin at the in black hole collisions, the gravitational waves that come off from that from perturbations of that final black hole in the final ring down, that they might actually probe the region extremely close to the horizon, and we might be able to see experimentally whether or not the space-time geometry there truly is that of the Kerr metric or it might be something else that's been modified due to the consequences of the information loss paradox. Just fairly recently, my hopes that might be the case, that we would get observational data of that sort from LIGO and LISA in the future have been dashed because it was been found, and this is work on papers by Maximilian Eso is one of the papers, recent paper that has shown that the gravitational waves are actually produced in a black hole collision, primarily at rather large radii, not near the horizon. The perturbations near the horizon all go down the black hole, and it's the gravitational waves are really coming from something like twice the size of the black hole, that region on outwards, if whatever can escape to infinity. And so it appears to me that we're not going to ever really be able to probe the vicinity of the horizon with gravitational wave observations, just because of the nature of these black hole collisions. The waves are not being emitted from extremely close to the horizon. They're being emitted from out some distance away from the horizon. Okay, so those are meandering thoughts motivated by your question.
Thank you very
Thank
much.
you. Thank you very much. Maybe the last question is Victor Mauricio Gomez González.
No se encuentra en la sala, doctor.
Okay. Okay, then Genaro Jorge Arturo Rojas Santana. Okay.
Nice to meet you, Professor Kip.
Thank you.
My question is, are we in the right way to be an interplanetary civilization?
So I didn't quite understand. Are we
in the right way to be an interplanetary civilization?
So is the question, are we likely to be able to carry our civilization out to into the solar system, you mean, or into the regions around other stars? I don't know.
Yes, around the stars.
Around other stars. So you mean an interstellar civilization?
Yes, I think this is the meaning of this question.
Okay. So first let me say that I do think it is fairly quite clear that we will have carry our civilization, humans, to small colonies on other bodies in our own solar system, and it may come faster than I had expected 10 years ago. I think that the dreams that Elon Musk in particular has in connection with SpaceX are not entirely unrealistic. It's a real possibility that in my lifetime we will have people on Mars, and that in this century we will have colonies on moons of Saturn or Jupiter. So I think that's realistic. It's likely to happen. Getting to other stars and the planetary systems around other stars is so extremely difficult because of the enormous distances involved that while I think if we do not destroy ourselves as a civilization, that I think it's likely that will also happen. It will be several centuries before it can happen. It's just so extremely difficult. Of course, it's really impossible to predict that far in advance. So all I'm doing is speculating based on the extreme difficulty that we see because of the enormous distances between the stars. But we know how to design brute force systems that would be able to go there. You have it in science fiction stories about colonies inside of large cylindrical spacecraft, say, like at the end of the movie Interstellar, that traveled between the stars, but taking many, many generations to do it. I think that is also possible. Whether humans will want to do that, I don't know. But that's it's something that is conceivable. And I think humans are likely to take up the challenge and do something like that in the longer term. But it's going to be centuries, not decades, until that happens.
Thank you very much.
Thank you, Kip. I just wanted to ask you if you're willing to answer a couple of more questions, or whenever you want to stop. Just.
No, I'm fine, Miguel. Sure.
Okay, so Tonatiuh, do you know what that next question is?
Victor, Victor Mauricio Gomez.
Yes, thank you. Hi, Professor Thorne. Gravitational waves and the shadow of a black hole have already been observed. Is there any feasible experiment to search for wormholes? Do you personally believe in its physical existence? Thanks.
I'm very skeptical that wormholes exist naturally. I don't see any way that they would form naturally, by contrast with black holes, where it's rather easy to form them naturally. So if they are allowed by the laws of physics, I think they almost certainly have to, with high probability, they have to be created by a very advanced civilization. So one can still search for them, but with an expectation that that they're not like to be out there in anything like the numbers that you have of black holes, because they probably don't occur naturally. But let me back up and say also that I have been proved wrong a few times about things that I absolutely were almost convinced of at the 99.9% level. And so I'm cautious about predictions like this, about saying what's possible and what's not. A good example was the accelerated expansion of the universe. The idea that there is something like a cosmological constant, or that gave rise to then an acceleration in the expansion of the universe. That just seemed to me so crazy that it couldn't be true. That when the first observational data came in and said it was true, I didn't believe. I thought there had to be something wrong with the observations. When the second set of data came in, I didn't believe. It required 3 independent types of observations before I believed in that. So my confidence in my predictions is it was rather shaken by that. Nevertheless, my prediction is that that these things have to be built by extraterrestrial civilizations. There has been some amount of analysis of how to see wormholes that I have not followed in detail. Search for wormholes through stuff that comes through them. And so I can't comment on the literature on this, but I think it is a respectable area of investigation. And there are Igor Novikov, for example, my dear friend, Russian astrophysicist with whom I've collaborated over the years, is a great advocate of this.
Thank you.
Thank you very much. The next question is from Aida Nava Bencheik.
Hi, this is Timothy Wofford, Aida's husband. So my question is about the delay of light and how do we interpret the equations of general relativity? How do we interpret the metric? So the delay of light says that when light passes a large mass, the amount of time that it's going to take to get from one side of the large mass to the other is going to be longer than expected, if you considered the space-time to be flat. And we can explain that delay of light in terms of a variable speed of light, depending on the gravitational potential it's going through. Or we could also describe it equally in terms of time dilation and length contraction in that region. On the other hand, particles that decay, they have longer lifetimes when they're closer to the mass than when they're farther away. And so to me, that sounds a lot stronger argument that time dilation and length contraction are the correct ways of interpreting that. But another logical conclusion is that whatever process that controls the decay of particles is mediated by some massless mediator. And so I was wondering, what are your thoughts on how do we interpret those equations, and what does that imply for particle physics and other things? Thank you.
So all observations of this sort that we have, and I think most speculations, can be explained by general relativity, which of course becomes special relativity in the absence of space-time curvature. And those equations of general relativity, however, can be interpreted physically in several different ways. And long ago, meaning 1980s, I came to realize that for purpose of research, that some research problems in general relativity are solved most easily and most quickly by interpreting things entirely in terms of curved space-time. And others are solved much more quickly, much more clearly, much more easily by reformulating the equations in the language of classical field theory in flat space-time. And so there are mediating fields that can be thought of as you go back and forth between the two descriptions, mediating fields that are pieces of the space-time metric in the curved space-time depiction. But field theory in flat space-time has enormous power, conceptual power and computational power for some problems. The elegant mathematics of curved space-time has enormous power for other problems. There's a mathematical mapping between the two different ways of writing relativity theory. And so the two different ways are mathematically equivalent, but they look very different, and you think about them very differently. And this brings me to Richard Feynman's messenger lectures at Cornell University that she gave back around 1963 or so, and that got written up in his little book, The Character of Physical Law. It's a wonderful little book in which he's basically talking about philosophy of science from the point of view of Feynman. How do you think about science? What points of view do you take on it? What is the epistemology? What happens when you have several different ways of thinking about the same pieces of physics? And he argues that there is enormous power in having different kinds of ways of thinking about the same thing that you may know are in some sense mathematically equivalent, but the mental pictures that you use, the diagrams you use, the words that you use, and the actual form of the equation you use are quite different in the two cases. Because one formulation may get you quickly to an answer where the other formulation may never get you to the answer because you can't work it out. And so That's a long-winded way of saying I don't think it really matters in a deep epistemological sense. It's not an interesting question to ask what is the truth as to which one is it, which way of describing things is really true. Rather, for me as a research physicist, the interesting question is which one is going to be most useful for the particular problem I'm trying to solve.
Okay, thank you.
Thank you very much. The next question is from Luis Ureña Lopez.
Yeah, hello, Professor Kip Thorne. Thank you very much for your nice talk. My question is, what are your expectations for gravitational wave astronomy in the near future? What would you like to know about the universe using gravitational waves, for instance?
So the thing that I think is most exciting for me is not, and a piece of the first step is in the near future, is seeing gravitational waves from the earliest moments of the universe, primordial gravitational waves, because we know from theory anyway, we believe from theory that gravitational waves coming from the early universe, from the earliest moments of the universe, the way they are created is something came off of the Big Bang singularity. That something we generally suspect as theorists is vacuum fluctuations of the gravitational field. But it might have been something else. It might have been some actual graviton, some actual gravitational waves. But whatever came off of the big off of this singularity, emerged from the singularity, will have been amplified enormously by the era of inflation, when the universe was roughly 10 to the minus 35 seconds old. And that amplification then makes the way, whatever came off the Big Bang strong enough that it is likely to be detectable by at least two different methods in the coming decades. One method is through the influence of these gravitational waves of very long wavelength on the polarization of the cosmic microwave background. This influence arises because the gravitational waves are stretching and squeezing the plasma whose electrons do the last scattering of the electromagnetic waves that make up the cosmic microwave background. And they're stretching and squeezing that the plasma at that moment of last scattering when the universe was about 300,000 years old. So the polarization pattern that you see in the cosmic microwave background carries a signal of the primordial gravitational waves, we think, so-called B modes. Those B modes have been seen, but they are contaminated by emission from dust and possibly synchrotron radiation from material in the foreground in the more modern universe, and uncontaminating them and seeing the actual B mode polarization of the cosmic microwave background that arises from the primordial gravitational waves is the holy grail these days. It's observational CMB research. I think it's likely that that will be sorted out within the next 5 to 10 years. I'm very hopeful about it. And that will be a huge, momentous thing, that if we see this polarization pattern and from it, we learn something about the spectrum, the spectral properties of the primordial gravitational waves, with wavelengths in this case, or periods of oscillation that are hundreds of millions of years. What you're really seeing is patterns with on the sky, where the wavelengths on the sky are hundreds of millions of light years on the sky in this polarization pattern. In the time frame around 2050, I expect that a successor to the LISA gravitational wave mission, something called Big Bang Observer, that's in the conceptual stages, that this will actually see directly the primordial gravitational waves with periods, instead of being hundreds of millions of years, there'll be periods of sort of something like 1 to 100 seconds. So enormously different periods from the ones that will be explored with the CMB. And if we have then spectral information about the gravitational waves in these two extremely different frequency bands, the primordial gravitational waves, they are going to tell us about a convolution that is a combination of the influence of quantum gravity in the Big Bang itself and the influence of inflation, because what you see in terms of properties of the gravitational waves that come off are a truly mathematical convolution of the Big Bang emission, whether it's vacuum fluctuations or whatever it is, and the influence of inflation. That's going to be extremely interesting, extremely powerful, I expect, for telling us about inflation and about the Big Bang and about quantum gravity. That's the thing I find most exciting among the prospects for the future. There will be a lot of other stuff that is also really very interesting, but that to me is the most exciting thing. I was born in 1940. I plan to live to age 110. I might well succeed given my ancestry and the genes I have. And I'm counting on that because I want to see both observations from both the Big Bang Observer and the CMB polarization before I die.
Hopefully so. Thank you very much, Professor.
Thank you. The next question is from Alfredo Rodriguez. Okay.
This is Arturo Fernandez.
Okay.
The question is about what you said at the end of your last question, the connection with quantum gravity. And as you said, this is quite challenging question and answer. My question is about the dark matter. Is it possible to have a connection with the gravitational waves and the dark matter? Possibility to have it? Yeah.
So it's possible. The most interesting thing of this sort that I know of is speculations by Lisa Randall, I think in particular, that some portion of the dark matter may, while it has extremely weak coupling to ordinary matter, may have rather strong coupling between different sectors or different species of dark matter. And as a result, you may then have the possible formation of dark stars, condensed objects made of dark matter. You may have dissipation between different species of dark matter that could cause some portion of the dark matter that's in the halos of galaxies through dissipation to settle down into the, say, into the inner parts of the plane of spiral galaxies. And so there's a thin concentration of dark matter in the plane of the spiral arms of galaxies. And you could have then sources that are concentrated in there that are associated with this condensed dark matter. And that somehow through gravitational wave observations, we could see those kinds of sources concentrated in the planes of spiral galaxies. I'm doing a lousy job, I think, of describing her ideas, but this is the essence of them, I believe. So these are very speculative, but I think they are also quite possible, and they give you some sense of that there may really be something there.
Thank you very much. Just the last thing, I didn't hear your comment about Barry Barish's contribution to this detection. Can you please tell us what he did?
Yeah, I'm very happy to. I jumped over all of this. I jumped from the very beginning to the very end of these instruments. I said it took about 50 years, 45 years, and it took 2,000 people. And magically, we wound up with these observatories. Well, it wasn't magically, it was through the genius of Barry Barish. The period between 1973, 72, when Ray Weiss had his first ideas for these interferometric gravitational wave detectors. Between then and the early 1990s was a period of struggling to conceive of LIGO, do a lot of R&D so that we had the technology nearly in hand to build interferometers. But it was a period in which we did not have the capability, well, during which we were discovering how extremely difficult this was going to be, discovering that success was going to require this to be changed from being small science into being big science. And we were working in small science mode, just beginning to make a transition toward big science, when fortunately, from our point of view, the superconducting supercollider got canceled and Barry Barish became available to become the director of LIGO. And that was just as we were at the point where we needed a superb director who knew how to create a organization, how to make major decisions that had to be made about precisely what direction do things go, technical decisions, and that could build detectors that, as I said before, are so complex that they have 100,000 data channels coming out of it. Detectors that could only be built by a team of 1,000 people. And that was Barry, and that was Barry's genius. He made key decisions about things like abandoning the argon ion lasers that were being used up until then and switching to neodymium YAG infrared lasers, despite the fact you can't see the laser beams. And so you're a little afraid you're going to get blinded by beams that you can't see. But major decisions that he made, and then created the structure of the LIGO scientific collaboration with the expanding beyond just Caltech and MIT to include what is now roughly 100 different institutions in more than 20 different nations to pull this off successfully. How do you pull it off with a collaboration that's tight enough to pull it off successfully when funding sources are scattered over a number of different nations, although the dominant funding is still from the US. I mean, it was just a huge challenge that I don't know whether anybody else could have really pulled it off in the end. Barry is, in my view, the most effective leader of large physics projects that the world has ever seen. And the high energy physicists seem to agree in the sense that once he had LIGO under control, fortunately, more or less pretty much under control, the first LIGO interferometers were beginning to operate. The high energy physicists came to him and said, we, as an international collaboration, we want to move forward with an international linear collider, the next generation of big instruments. And this involves all the major nations of the world collaborating. And the only person we can agree on to lead the design work is you. If you don't do it, it probably won't happen. And so he left us temporarily to lead that design work, and then came back to LIGO. But I mean, he really is the genius that pulled this off. And I think for the first time in history, when the Nobel Prize was given, it was shared by the person who pulled it off as the organizational leader, along with the people who were involved in founding the project and the initial ideas. And so, I mean, that is really quite something that the Nobel Committee finally came to realize, that this is an absolutely crucial piece of pulling off this kind of scientific breakthrough, this kind of leadership. And so, yeah, that's my response about Barry Barish.
Thank you very much. Wonderful talk.
Thank you.
Thank you. Maybe the last question, Professor Thorne. Okay.
Yes.
Okay, Victor Arriaga. Okay, Victor.
His microphone seems to be off.
Yeah, turn on your microphone. Victor.
No.
You have to turn on your microphone, Victor.
Well, if he can't do it, maybe I can ask the question. He wrote it on the chat.
Okay.
So Victor Arriaga asks a very different question. What was your experience working in the movie Interstellar?
So it was a wonderful experience. The best part of this was brainstorming with Jonah Nolan and Christopher Nolan, and before that with Linda Oakes, about the science to go into this movie. It's a collaboration, well, and then brainstorming with the visual effects people, with Oliver James, with Paul Franklin, about getting the visual effects right. I find collaborating with people whose backgrounds are very different from mine, who bring to it insights that I would never have had, is really fun and really productive. And that was what I got out of this brainstorming with these people. The other thing that really struck me was on this movie was that everybody involved in the movie, from the young man who parked my car when I would go onto the Warner Brothers set, to the top executives at the studio, everybody was really enthusiastic about making a movie that was based on real science. And I was just known as the science guy from at all levels in the movie. And seeing that enthusiasm in Hollywood for real science was just absolutely wonderful.
Thank you, Kip. So it's almost 8 o'clock here and 6 o'clock for you. So I think with that last question, we can finish. I just wanted to thank you again for this wonderful talk and for being here with us in the Mexican Physical Congress. And we hope to see you again very, very soon, sometime here physically in Mexico, as soon as you can and as soon as this pandemic ends. But thank you very much again. I think Tonatiuh will probably arrange with you an interview then tomorrow.
Yes.
Yes. Yes, maybe we can talk about maybe at 9 o'clock or 10 o'clock.
What you just email me. You also
Okay.
have my telephone numbers as well. So
okay.
So and I'm at your disposal whatever time you want.
Okay. Okay. I understand. Yeah. Thank you very much for the nice conference. It was amazing. Thank you very much. Yeah.
Great questions. I thank you all for these wonderful questions, and it's been really enjoyable. Thank you.
Thank you. Okay. Bye bye. Thank you very much.
Bye.
Gracias a todos por la presencia. Hasta luego. Muchas gracias por su presencia.
Gracias.